Hey everyone, I am Miss Hu, your physics teacher. In this video, I will be discussing the answers to a past year question and then we will compare the answers to the mark scheme. For some questions, the answers will be covered first so that I can explain the thought process of getting to the answers, as you will need to know how to get the answers and not just what the answers are. Then, based on the mark scheme, I'll explain why the marks are awarded as such. Question 9. Strontium-90 is a radioactive isotope that contains 38 protons and 52 neutrons. Strontium-90 decays to form an isotope of yttrium by emitting beta particles. A1. Suggest how the nucleus of a stable isotope of strontium differs from a nucleus of strontium-90. Explain your answer. So the question is very specific. They want you to suggest how the nucleus of the isotopes are different. So let's consider what's in the nucleus. There are only protons and neutrons, correct? You cannot talk about anything else except about those protons and neutrons. So let's look at what's different. Now, for the same type of element, they have the same number of protons. That means that all the isotopes of strontium have the same number of protons. That means what's different is the number of neutrons. So our answer has to involve neutrons. Now remember that the nucleus of a radioisotope has excess neutrons, and these excess neutrons is what makes it unstable. The question is asking us to suggest how the nucleus of a stable isotope of strontium differs. So you need to talk about the stable version and not the unstable version. So the unstable version has excess neutrons, so we can write that the stable isotope has less neutrons. And the explanation for this, let's talk about the unstable version here. Radioactive isotopes. I'm going to write this in full because the question used the term radioactive isotopes have excess neutrons. So let's check the mark scheme, and you can see that in order to score the 2 marks, you have to mention both that the stable isotope has fewer neutrons or less neutrons, and radioisotopes have excess neutrons. Alternatively, you can also write that the stable isotope has fewer neutrons and radioactive isotopes are too heavy. The word too is underlined here, which means that word must be present. If you only wrote that radioactive isotopes are heavy, it won't be accepted. Now, if you were to just write that the stable isotope has fewer neutrons and you didn't give the correct explanation, you can still get 1 mark. Or if you wrote that the radioactive isotopes have more neutrons or that they are too heavy, that's 1 mark for the correct reason. If you only wrote one of these, you will still get 1 mark. You just won't get the full 2 marks if you missed out the other sentence. Now, let's look at 2. Complete the nuclide equation for the decay of strontium-90 to yttrium. So they've given us the equation in AZX form, starting off with 9038 SR, which will decay into Y and beta. You're required to fill in the blanks of these numbers here, which are the values of the nucleon number and the proton number for yttrium and beta respectively. So to figure this out, you of course must know how to fill in these numbers for the beta particle. And beta is 0 minus 1. From here, then, we can figure out the value for the other blanks, which is 90 on the top of yttrium. And this will become, of course, 39. So if you check the mark scheme, you can see that 1 mark is given for 90 and 39 for yttrium, and 0, -1 for beta. So that's how we get the 2 marks for this question. Number 3. Explain why scientists limit the amount of time they are exposed to radioactive strontium. Now remember that radioactive isotopes are dangerous because they produce ionizing radiation. And what's the problem with ionizing radiation? They are very harmful to human beings. So that's the accepted answer because you can see in this question, they never mentioned anything about ionizing. So if you wrote the word ionizing, it's quite likely you would get 1 mark for this question. So let's write that here. Radioactive strontium produces ionizing radiation, which is harmful to human beings. Let's check the mark scheme. So you can see in the mark scheme here, the word ionizing is underlined, which means that you must use the term ionizing in your explanation. You must also mention that it is harmful. That's how you get the 2 marks. So although it might look like just one sentence, it's actually made up of 2 parts, ionizing and harmful. That's why you'll get 2 marks. So that's why it's one sentence here in this mark scheme. Alternatively, you could write that beta particles are ionizing and harmful to humans. So it's still pretty much the same thing, except that instead of just mentioning radiation in general, if you mention that beta is ionizing, you still get a 1 mark. The key thing here is you must mention that it's ionizing and harmful. Now, what could cause you to only get 1 mark? If you only wrote that radiation or beta particles are harmful, or if you wrote that beta particles ionize, or if you wrote that it ionizes and is harmful, you only get 1 mark. So why would this only be worth 1 mark and not 2 marks? If you only wrote as ionizing, it's not clear why they shouldn't be exposed to radioactive strontium. So clearly you must write that it is harmful. You have to explain why they should limit their exposure. But if you only wrote why they're harmful, it is not clear what makes them harmful. So that's why you need to write both ionizing and harmful. The reason why, if you wrote ionizes and harmful, you only get 1 mark instead of the 2 full marks is because the term ionizes here is not the same as ionizing radiation. Ionizing radiation here means that the radiation produced, in this case beta, causes ionizing effects. If you wrote it ionizes, it makes it sound like the radioactive strontium is producing the ionizing effect, which is not true. The radioactive strontium produces radiation, which has the ionizing effect. So that's why you won't get 2 marks if you wrote it this way, because technically it's not entirely correct. Now let's go on to B. Yttrium is also unstable. A scientist places a sample of yttrium near a radiation detector. Table 9.1 shows the count rate recorded by the detector as the sample decays. So you can see in table 9.1, we have the time and the recorded count rate with the units counts per minute. Figure 9.1 shows a graph of the count rate due to yttrium against time. So we have a graph where the count rate due to yttrium with counts per minute on the y-axis and time in hours on the x-axis. 1. Use figure 9.1 to determine the half-life of yttrium. Show your working. So in order to determine the half-life from the graph, you need to find out the starting value of the count rate, and we need to take the time it takes for the count rate to drop to half. But you have to check whether the graph is a corrected count rate or does it include the background radiation. So how do we verify this information? There's already 2 hints in this question. First of all, the question already tells us that figure 9.1 shows a graph of the count rate due to yttrium. They've even bolded this to point out to you that this graph is only due to this radioisotope, which means that it has already been corrected. It does not include the background radiation. A second hint which you can use, which is not in all questions but exists in this question, is to check against the table of data. So this is one of those rare questions which not only has a graph but also has the table of data. You can see that in table 9.1, the recorded count rate starts from 68 counts per minute, but this graph starts from 48. The difference obviously is because it has already deducted the background radiation. So to get the half-life, you don't have to minus the background radiation. We can just start from the number of 48 and look for the time it takes for 48 to drop to become half. So half of 48 is 24. Now we will need to draw the lines on the graph to show how we got the value, because the question says show your working. Whenever you're looking up any values from the graph, to show your working here means you must draw the dotted lines to show how you were able to interpolate the data or to get the value from the graph. So the count rate we're looking for is 24. You should be using a pencil and ruler for this, by the way. And we're going to use the graph to find out how much time it took for the count rate to drop to become half. Okay, this looks terrible, so I'm just going to fix it. So this is why you should use a pencil and ruler. Don't draw freehand. I'm drawing freehand because my tool doesn't have any straight lines. So from here, based on my observation, this value is about 76 hours. So I'm going to write here 76 hours. Now they've given us a lot of space here, which means that if possible, you should also show your working. So one way to show your working here is to show that you're looking up half the count rate. So the starting count rate was 48. We divide it by 2. So we need to look up the value for the time to drop to 24 counts per minute. Now let's check the mark scheme. So the mark scheme is quite lenient here. They accept a half-life value from anywhere between 72 to 76 because actually if you zoom in, you'll find that the value for 24 counts per minute is somewhere in between. So as long as you get the number between 72 and 76, you would still get the full 3 marks in this case. Now, what if the value of your half-life is outside this range? You can still get marks if you show evidence of the count rate being halved, which is why we need to write this 48 divided by 2. And you should also show evidence on the graph or the working that is used to find time for count rate to halve. So by drawing the lines, you can also get another mark. 2. Explain the difference between the count rate in table 9.1 and the count rate due to yttrium plotted on the graph in figure 9.1. So earlier, I actually gave you the answer for this question already. But the reason why I talked about it earlier is because it is quite important to know whether the graph is corrected or not before we do any half-life calculation. So clearly, there is a difference between the numbers on the graph and the table of data because the table of data includes background radiation while the graph is already corrected. That means the graph does not include the background radiation. So I'm going to write it out as an explanation over here. The table includes background radiation. Now that should be enough to get you 1 mark, but I'll just write some other variations of the explanation so you can see that there are other ways to explain this answer. You can mention that the graph does not include background radiation, or you can say the graph is plotted based on the corrected count rate. The term corrected count rate means the background radiation has already been deducted. It is an actual term in the radioactive industry. So now let's check the mark scheme. So the mark scheme accepts the answer from anyone from below. Table includes background radiation. You must have the word background. That's why it's underlined. Graph does not have background count rate. Again, the term background is underlined, which means it must be present in your answer. Or you can mention that the graph has corrected count rate. The word corrected is underlined because it must be present. So any one of this would give us the 1 mark. I forgot to award myself 3 marks for this question just now. And that's how we solve question 9. If you found this video to be helpful, click like and subscribe. And do let me know how you have found this video to have helped you. To watch videos on other questions, check out the playlist on my YouTube channel or on my website, physicsrocks.com, to find the question that you are looking for. If you have any requests for a particular question, drop your request in the comments below, stating the year, month, variant, and question number. And if I haven't covered that question yet, I will do my best to come up with the explanation video as soon as possible. All the best for your examinations!